All right, so we're going to learn a little trick here called the descent of symmetry. And so suppose you have a problem, determine the normal modes of these three different molecules. So we have chloromethane, dichloromethane, and chlorofluoromethane, right? So you could do this right now with all the skills you have in a very similar way that you did for methane, right? So you would determine the stationary atoms, determine the representation for X, Y, Z on the central atom, and proceed from there, reduce the representation, subtract off the rotational modes, subtract off the translational modes, and you would be good. And if you wanted to, you could figure out which ones were even IR active, right? There turns out in a lot of cases to be a faster way, especially if you've already done some legwork in calculating a higher symmetry analog of the molecule. And that's what this section of the lecture is about. And so that's what we said. You could do it the long way. The easier way is to use results from methane and then do what's called descend symmetry, okay? So if you look at these molecules, they're all analogs. Methane is the most symmetric. That's going to have point group TD. It's totally tetrahedral. Chlorofluoromethane has a point group C3V. Basically, there's a C3 running through the carbon-chlorine bond, and the bottom three H's form like a tripod, and so that's fine. And then CS, that's going to be the symmetry of chlorofluoromethane. That only has a mirror plane. That point group only has identity in a mirror plane. The mirror plane, you can see, is right through the chlorine, carbon, fluorine group there, and that's the mirror is gonna cause the two hydrogens to interchange. So if you look at the character table for all these point groups, an interesting pattern emerges. And that is that we know that C3V is sort of a subset of TD, right? It's less symmetric, but the characters are this way. So check this out. In tetrahedral, you have the following symmetry classes. You have identity, you always have identity, C3s, C2s, S4s, and sigma Ds. In C3V, all you have are E's, C3s, you have fewer of them, you have 2 instead of 8, and you have mirror planes. They're redefined to be called sigma V's here, not sigma D's. But what you'll be able to see is that all the characters for E, right, 1, 1, 2, those transpose. For 1, 1, negative 1, 1, 1, negative 1, 1, negative 1, 0. So the whole character table C3V is a subset of TD. And you can go even further, right? For CS, you only have a mirror plane here. It's called sigma H. There's only really one mirror plane, so it doesn't really matter what you call it. But by convention, we call it sigma H. And identity. And again, those have those characters are a subset of C3V. You'll see the molecule symbols change slightly. Here you have primes instead of 1s and 2s because you no longer have a principal rotation axis. You only have sigma H. But all these things are true, okay? And so we call this a subgroup. So CS is a subgroup of C3V, and C3V and CS are subgroups of TD, right? So what you can do is you can derive what's called a correlation table. So it tells you how a certain symmetry, how an irreducible representation in a higher symmetry translates down, how it will transform down in a subgroup. Okay, so let's do this for, let's derive the character table for TD going down to C3V. We're descending in symmetry. So first, starting with A1. A1 in C3V, we have the character is 1, 1, 1, right? And you can see that we have E1. If we have an A1, right? In TD, let's go back. Okay, so A1 in TD is going to be, if we look at C3V, we have an E. Let me use the pointer here. You have an E. 1, 1. So we put a 1 down. C3, 1. Corresponding, this should be really clear. Use a different color here. C3, the corresponding symmetry element, the closest thing there is the C3, right? So that 1 is going to come down here. And lastly, sigma V. Sigma V is sigma D there. So we have a 1, okay? If you go through this for A2, all right, we had a 1 and a 1 for E. For C3, we had a 1 and a 1. This is all seeming pretty easy, right? And negative ones. Well, A2 is going to be A2. Okay, E, again, these ones are simple. You'll see here, though, in a second, something different will happen. With T1, so now we're asking the question, if we have T1 and TD, how does that translate in C3V? Well, you can see there's no T1 in C3V, right? So what are you going to do? Well, you're going to look at, all right, I have a 3, I have a 0, and I have a -1 in the classes that I care about that translate. So then what you're going to have to do is you're going to have to take that reducible representation. That's not equal to any of these. That's a reducible representation. So you're going to have to reduce that. And if you do that, you can find using your formula, or this is simpler enough, just do by inspection, right? A2 plus E, right? 1 plus 2, that's going to get you 3. 1 plus -1, that's going to get you 0. 1 plus 0, that's going to, -1 plus 0, that's going to get you -1. I used the wrong one here. A2 plus E. A2 plus E. 1 plus 2 is 3. 1 plus -1 is 0. And -1 plus 0 is -1. Okay? So what that means is T1 and TD translates into A2 plus E in C3V. We can do a very similar thing with T2. T2, we have 3, 0, and 1. And that ends up being A1 plus E. So T2 in TD translates as C3V. So you can come up with this correlation table in this way, where you say, hey, I have my TDs. How do they translate into C3V? We're translating languages here, right? So how do you use this? Well, this is where it gets pretty easy. Now I have a correlation table I'm just giving you, not only TD going to C3V, but TD going to C2V and TD going to CS. So we can ask, well, for chloromethane, we know, well, first of all, for methane, we know that we derived A1 plus E plus 2T2. And so this is a lot of work went into this, right? But now we get to use the fruits of our labor here for some other related molecules that are lower symmetry, right? So chloromethane down here, that has symmetry C3V. So all we do is say, hey, we have A1, TD, how does that translate to C3V? A1, put it down. E, how does that translate in C3V? E, put it down. 2 T2s, how does 1, 2 T2 translate in C3V? A1 plus E, so 2 times that. Multiply that all out and you get 3A1 plus 3E. Those are your normal modes. You could go on to figure out which ones are IR active if you wanted to. Dichloromethane, C2V point group. So you say, okay, I have an A1 starting from methane, that translates as A1. I have an E, that translates as A1 plus A2. So I'm gonna put those down here, right? I have 2 T2s, each T2 translates as A1 plus B1 plus B2. Just reading off the table here that we made. And so you can add all those up together and get that your normals are 4A1 plus A2 plus 2B1 plus 2B2. Lastly, we can do this for chlorofluoromethane. That's symmetry CS. And so again, A1 goes to A prime, E goes to A prime plus A double prime, that's right here. And then you have your two T2s, each T2 goes to 2A double prime plus A double prime. Multiply this all out, you get 4A prime plus 5A double prime. So an important thing to realize here is kind of, you didn't change the number of atoms. That's why this works. And all you did is you sort of did kind of like a ligand substitution. You changed one of the atoms to break the symmetry to something lower. And remember that this has 9 normal modes. Some of them are degenerate, right? It's only 4 with unique energies, but this has 9 because we have 2 times 3. T2 is triply degenerate. That's 6 plus 2. That's 8 plus 1. That's 9. So you can't be destroying normal modes here. There's the same number of atoms. They're all non-linear. So it's going to be 3n minus 6 normal modes, and you have 5 atoms in each. So 3 times 5 minus 6 is 9. But you can check all these have 9 normal modes. Here you have 3A1 plus 3E. Each E is doubly degenerate. That gives you 6 modes plus 3A1s. That gives you 9. Here you have all singlet degenerate ones, and you have 4, 5, 7, 9. Here also you have 4 and 5, 9. So that all checks out nicely.